Okay, I want to welcome everybody back to the next week, week 2 of our video series to help you pass the CET. How did you do with the first week's material? Did we do okay? I'm hoping so. I'm hoping everybody did okay. So, are you creating a test bank? Before you start watching this video, I would recommend that you have the week 2 handouts along with the practice quiz before you get moving. If you don't, go ahead and stop the video and go back and print them out, or take some really good notes on your own. It's up to you. Alrighty, let's go ahead and move on here. And this week's topic will be about standard components. What I mean about that is inductors, transformers, and capacitors, and how they react typically with DC voltages and currents. So that's what today's video is about. And we're going to hit all the highlights of that and talk about some of the language that you might run into on pre-employment screening exams and the Certified Electronics Technician exam. Now, if you are not interested in taking the CET exam, all that you need to do to pass this course is to pass 6 of the online quizzes and take the program outcomes final exam and get a 60% on it. And so that's what you need to do. So other than that, if you want to take the CET, it always looks good on your resume. We're going to ride it out for about 8 or 10 weeks, and we'll have the option to take the CET exam at the end of the quarter. We'll schedule it for you. So get your first activity, and we'll talk about capacitors first. What does the word capacitance mean to you? Well, capacitance is the ability to store an electric charge. Typically, the main considerations that determine the amount of capacitance in the capacitor are the size of the plates and the distance between the plates. What happens to the total microfarad capacitance of a cap if the plates are made bigger or smaller? Well, the bigger the plates are, if the plates go from small to large, we can actually store more electrons on there, so it means it can store more capacitance. And how is the distance between the plates related to the capacitance? Well, if the distance increases between the plates, you're going to have less strength in the electrostatic field between the plates, and therefore this will have less capacitance than that. So, 2 important considerations here regarding capacitors are what about the size of the plates and the capacitance? The bigger the plates, the more the capacitance. The smaller the plates, the less capacitance. And what about the distance between them? If the plates are very close together, they can attract more electrons. That would be more capacitance. If the plates are further apart, that would be less capacitance. Now, of course, we know that capacitors typically are not rated in farads. They're generally rated in pico, nano, and microfarads. You rarely see a millifarad or just plain farad capacitor, although they are available sometimes in high-power car stereo systems. An old unit that you might see in a CET exam is a very old unit called the microfarad or micromics. When you see that, all that is an old unit for picofarad, because picofarads are 10 to the minus 12th power, and microfarad is 10 to the negative 6. So if you have a microfarad or a micromic farad, that would actually be 2 10 to the negative 6s, and that would be 10 to the negative 12. So it's just an old term for picofarad. So in case you run into that, a capacitor that's rated in 5 microfarads typically would mean that it's 5 picofarads. I haven't seen that one for a while, but you just never know. You never know when you're going to see that. That's kind of an odd one that appears every once in a while. Now, how do you find capacitance of caps in parallel? Well, here we have 3 capacitors in parallel, and when you string them together with this wire, you're essentially increasing the size of the plate when they're wired in parallel. So to find values of capacitors in parallel, you simply just add the values together. If this is a 1, 2, and 3 microfarad cap respectively, it'd be 1 plus 2 plus 3, and what would that be? 6 microfarads. So that's how you find capacitors in parallel. So if 3 caps are connected in parallel, 200, 200, and 100, you just simply add them together. That would be 500 microfarad. That would be the overall capacitance. And sometimes the questions on the exam will have a 2-part question. For example, capacitors in parallel are calculated the same way as resistors in blank. And so you'll have to actually answer that question. Well, capacitors in parallel, you just add them together. What kind of resistors do you have to just add them together? Well, that would be series, wouldn't it? So capacitors in parallel are calculated the same way as resistors or inductors in series. Now, how do you find capacitors in series, though? Well, capacitors in series are found the same way as resistors in parallel. So you need to use the reciprocal formula. Here's an example right here. I have 2 capacitors in series. I got C1 and C2. I take the reciprocal of C1 and add it to the reciprocal of C2. Make sure I hit the equal sign and hit the reciprocal key. You know the reciprocal key on your calculator. It's 1 over x. Now look at this problem right here, typical problem. 200, 200, and 100 microfarad. There's the diagram. Label these. Well, I can take the reciprocal of 200, the reciprocal of 200, the reciprocal of 100, hit the equal sign, take the reciprocal, and I would get the answer. If I did that, I would find it would be 50. But look at this. Here's how I would think about this. C1 and C2 are in series with each other, and they're both 200. If you do those two capacitors in series, that would give you 100. 2 100 microfarad caps in series would be 100. So these together are 100. Then you have another one in series with it, which is 100. So 100 in series with 100 gives you 50. So capacitors in series are calculated the same way as resistors in parallel. Now, every once in a while on the CET exam, I've been seeing this problem come up. It could be flipped over, it could be pictured as it is. They'll give you 2 capacitors in parallel, which you'll have to find these 2 capacitors in parallel first. Simply add them together. And this becomes one big capacitor, which is in series with this. So what is the value of C2? C2 is 10 microfarad. What is the value of C3? C3 is 40. So 40 plus 10 would be 50. So these two together make one capacitor, which is actually 50 microfarads. So here I have 50 microfarads. And here I also have 50 microfarads. And this is when it's not too bad, because we know that 50 microfarad in series with 50 microfarad is actually 25 microfarads. So the total capacitance of these right here is 50, because I'm adding C2 and C3, 10 and 40 microfarad. And then I have that in series with a 50 microfarad. So 50 in series with 50 would be actually a 25 microfarad. Now, these aren't going to be the same values, but I'm certain you're going to see a problem like this on your employee entry examinations or the CET exam. Now, here's an interesting aspect about capacitors in series. And whether it's DC or whether it's AC, what we find is that the capacitor that has the smallest value of farads will always have the larger voltage. And the reason behind that is that a larger capacitor has what appears to be a lower number of opposition to the actual flow of DC or AC through it. And therefore, The smaller cap will have more opposition and will gather more voltage. The reason behind that is that it deals with charge in the series circuit, and in the series circuit the charge is the same. But we know that the charge divided by the size of the plate, or the farad value of the capacitor, gives you the voltage. And so if you have the same charge on both capacitors, and the farad value is bigger on the other, the one with the bigger value will have the farad value in the denominator, and that will work out to be a higher voltage. So when you're faced with this, you always want to make sure that when you see capacitors in series, the smallest capacitor will always have the larger voltage. This is very important. You will see this question on the exam. So just look for the answer that shows the larger voltage on the smaller capacitor. That's what you need to know. There is math to solve this. There is math to be able to solve this problem, but you don't have time to solve it. Just look for the capacitor with the smaller value. In the field, the application of this would be such that if you have to replace a capacitor that's in a series bank, you would always want to make the smaller capacitor at least equal to the working voltage of the voltage that is applied. Because the smaller the capacitor, the more voltage of the source it will gather. Interesting aspect there. Now there's two ways that capacitors can be specified on very, very tiny ceramic discs. For example, you can have what we call the 3-number code, which you see here, and you ignore the letters and just look at the 3 numbers. The 3 numbers here would be 331. Sometimes this letter over here is a K, which makes you kind of confused about it, because K you think is being kilo. No, these letters are just tolerance when you see them. Ignore the letters. Look for the 3 numbers. That's all that you're trying to find. When you have a 3-number code, you find the number. And the first 2 numbers for 331, 33 would be the first numbers of the value of the capacitor. And then the 1 would be 10 following it. The third number tells you the amount of zeros that follow it. And this 3-number code is called the picofarad code. So this would be 330 picofarads. If you need to change it to microfarad, you move the decimal places 6 places to the left. But first you should go to nanofarad. So this would be 0.33 nanofarads. And I would move it 3 more places for microfarads. Micros times 10 to the negative 6. And what would that be? Let's see, that would be 0.00033 for microfarads. So they might give you a 3-number code, and they might ask you what is the value in pico, nano, or microfarad. But remember, the 3-number code is in picofarads. Now another way that you can actually see the farad values in a code would be as you see over here. Over here, you only have 2 numbers. If you only see 2 numbers on the capacitor, that is the value in picofarads. So that's the actual value. A 2-number value is the actual value. So what would this be? This would be 47 picofarads. This would be 27 picofarads. So for small ceramic discs, if you have a 3-number picofarad code, the first 2 numbers tell us the value, and then the last number tells you the amount of zeros on the end. In this case, this would be 330 picofarads. But what about this one, a 154? Oh, a 154, that's interesting. A 1 and a 5 for the first numbers, and then 4 zeros after it. 1, 2, 3, 4. So that would be 150,000 picofarads, because the 3-number code is in pico. And how many nanofarads would that be? Well, that would be 150 nanofarads, because I moved the decimal place 3 places to the left. And then how many microfarads would that be? 3 more places. That would be 0.15. All right, so that would be the 3-number code. 3 numbers, you got to do the picofarad code. 2 numbers is the actual value of the capacitor in picofarads. All right, get and look at this handout here, the charge-discharge RC time constant curve. I think I put that in your handouts, but here's what it looks like. Here's what it kind of looks like right here. So what this is showing you is whenever you put a capacitor in series with a resistor, it always takes a certain amount of time for the capacitor to fully charge or fully discharge. That's what this is what it's getting at. We've covered this material in second quarter, charge-discharge RC time constants. During the charge cycle, it takes one time constant, not seconds now, one time constant to charge the 63% of the source. So if this was 100 volts right here, and this capacitor started out at 0 like you see here, when I close the switch, after one time constant, the capacitor would charge to 63%, or 63 volts if this was 100 volts. Okay? Now, for a discharge cycle, the capacitor starts at the full voltage right here, the green curve, and when you close the switch, it begins discharging. And after one time constant, we'll talk about that in a moment, the capacitor will discharge to about 37%. So you need to know for one time constant for discharge it's 37%, for charge it's 64%, 63%. Those are the ones you're probably going to be checked at. The first time constant and the fifth time constant. Don't worry about 2, 3, and 4. If you know the first and the fifth, you're going to be okay. Now here's some interesting aspects about the first and the fifth time constant. During the first time constant, when it's charging or discharging, there's a lot of current flowing in that circuit. During the fifth time constant, there's very, very little change or any current moving. So when you charge, after 5 time constants, the current goes to 0, but the cap receives full voltage. When you discharge, you get a lot of current at first, just like charging, but after 5 time constants, it goes from the full voltage to 0 voltage. And there's about 2 or 3 questions on the time constant in the CET exam, and that's about 3 or 4% of the over 100 questions. So, first of all, what is an RC time constant? Well, an RC time constant is a time period in seconds, and you find it by multiplying the resistance of the circuit times the capacitance. So the resistance times the capacitance gives you one time constant. How is time and capacitance related? Well, they're directly related. The bigger the value of R and the bigger the value of C, the longer it takes for that capacitor to react. Now this is time constant T. T is the one time period. So going back to this is not 1 second right here, it's 1 tau right here, time constant tau. So this value in seconds would be equal to R times C. This value in seconds over here is not 5 seconds, but 5 times R times C. Okay, what is the time constant for a 47 microfarad and a 1 megaohm? Well, all you do is you multiply 47 microfarad, let me see, 47 EE6 negative times 1 megaohm, 1 EE6, and I get 47 seconds. So 47 microfarad times 1 megaohm gives me 47 seconds. What you see on your calculator is 47 seconds. What does that mean? Well, if I look back here, if this is 47, if this is 1 megaohm, this is 47 microfarad, this time period from here to here would be 47 seconds. And then from here to here for full charge or discharge would be 5 times 47 seconds. Don't confuse time constants 1, 2, and 3 with exact seconds 1, 2, and 3. Every RC combination is different. All right, how many time constants does it take to reach steady state conditions if no current flows? for the capacitor to reach full charge or completely discharge? Well, that would take 5 time constants. So number 4, your answer would be 5 time constants. But for number 4, use the values in number 3. Well, we said it was 47 microfarad, 1 megaohm was 47 seconds. So 47 seconds, because that's R times C, that's where we get the 47 seconds from. Whoops. Okay, that would be R times C. So 47 seconds. Let's see, 47 seconds, which is actually R times C. That equals 1 time constant, or 1 tau. And 1 tau in this case would be 47 seconds. Now it takes 5 time constants to completely charge or discharge. So 47 times 5. What is that? 47 times 5? It would take 235 seconds. 235 seconds. Seconds. Make sure it's a seconds, not 5. Okay. Now, which time constant, to make your life easier, which time constant will you be tested on? They're always going to test you on the 1st or the 5th. The 5th time constant, it completely charges the source voltage or completely discharges to 0 volts. That's no current flowing at that time. That's what we're getting at number 4. But the 1st time constant, you have to be aware that during the charge cycle, it will rise to 63% of the source. During the discharge cycle, it will fall to 37% of what it was charged to. So during the charge cycle, what percent of the total voltage appears on the cap after 1 time constant? Well, first you notice it's a charge cycle, and I can tell this is a charging circuit because there's a source there. The answer for that one would be, what would be the answer for that one? Well, let's back up and take a look. Right here. Right here, 63%. So that would be 63% of the source. What does that mean? After 1 time constant that you figured out up here on the top, after 1 of those, the voltage on this cap over here, the voltage on this cap would be 63% of that. If that was 10 volts, it would be 6.3 volts. 100 volts, 63 volts. 50 volts, well, half, 63% of 50, whatever that would be. Okay, during the discharge cycle, what percent of the total voltage is left after you begin to discharge? Well, the total voltage on the cap starts with some value, and then at 1 time constant during discharge, it will drop to 37%. So it's 37% of what the capacitor was originally charged to. And here's a really good example right here. This is a typical problem you will see on the test. Okay, look at the important information here. A cap was charged to 100. This cap was 100 volts. It discharges in 7 milliseconds to 37 volts. Okay, well that's a hint. Here's 100 volts, and it discharges to 37. Well, what percent of 100 is 37? Well, ironically, it's 37%. That means how many time constants? 1. 1 time constant of discharge is 37%. So right here, I know by looking at these two numbers, I'm dealing with 1 time constant, tau. So 1 tau in this case is equal to R times C. Now you got to pick out some other information. What is the amount of time it takes for that to happen? Well, look, 7 milliseconds right there. So put the numbers in. I put the numbers in, 7 milliseconds, 7 milliseconds. And that's equal to R times C. Well, what's given? Is the R given or is the C given? Well, I can see here the R is 4.7K, so put it in. 4.7K. So 4.7K times the value of C gives me 7 milliseconds. Well, how would I solve that? Come on, basic math. 7 milliseconds, 7 EE, 3 negative, divided by 4,700 ohms, and that gives me the capacitive value. Make sure you put it in engineering notation, second 6 if you haven't. So what value is that? Well, that would be 1.49 microfarads. Now I'm pretty sure that sounds like an odd number. Let me see. Let's check our work. How can we check our work? Well, 1.49 microfarads times 4.7K. Let's see if we get 7 milliseconds. So 1.49 microfarads times 4,700 ohms. Yeah, 7 milliseconds. Okay, so that's the correct answer. The correct answer for that would be 1.49. Okay, so let's just review that. First, I identify it as being one time constant, tau. One time constant, tau, is equal to R times C. The amount of time for that is 7 milliseconds. I put it in. The value of the resistor is 4.7K. Now I need to solve for C. 7 milliseconds divided by 4.7K is the value of C. Okay, how about this one? This is a charge cycle, number 9. Look, my source voltage here is how much? It's 100. And here they're asking, what value resistor would you need to charge a 300 microfarad cap to 63 volts? Well, that's a charge cycle. 63 volts over 100 is what percent? Well, you guessed it, it's 63%. 63% is 1 tau. Again, 1 tau is equal to R times C. You notice both of these problems revolved around the first time constant. They're only going to check you on the first or the fifth time constant. So what do? You take the time, 6 seconds, and you divide it by 300 microfarad. That will give you the value of the resistor. Let's see, 6 seconds divided by 300 microfarad, 300 e to the 6 negative, and I get a 20K resistor. So my answer for this would be 20K. Why? Because 20 kiloohms times 300 microfarad equals 6 seconds. So that's a charge cycle. All right, your next activity, basic inductors. Well, what are a few other names that you're going to run into for inductors? There's a couple of odd names. You might hear them called coils, because when you look at these things, you can see coils of wire. Look at that, coils of wire. You'll hear them called inductors. You'll hear them called chokes, C-H-O-K-E-S. A really old name is reactor, a reactor, but you don't hear that too often anymore because of nuclear reactors. So chokes, inductors, coils, sometimes you hear it called an RFC. An RFC, that stands for radio frequency choke or radio frequency coil. So it could be that. Those are all the different names that you might see on a test. Now, how do inductors react to AC current and voltages? Well, we know that X sub L, reactance in ohms, is equal to 2 pi FL. Okay, so anytime you have AC current, anything above 0 hertz, you're going to have some value of frequency in there. And that will cause it to have a certain amount of ohms. And that ohms actually hinders or impedes. Impedes is another word that you might see. Impedes, that is The same as meaning it's opposing the flow of AC current. So watch for that. It's kind of an older word that older engineers will use, impedes the flow of current. What determines the amount of energy that can be stored in an inductor, or the amount of inductance of an inductor? Well, there's two things. First, the amount of energy is determined by the number of turns. The more number of turns you have, the more magnetic flux you can generate. And the closeness of the turns. That would be the second thing. If the turns are very, very close together, you're going to have more inductance. If the turns are further spaced apart, you're going to have less. So look at this one. This inductor has a few turns, and they're spaced very, very far apart. This one has a lot of turns, and they're spaced really, really close. Which one of these would have the larger inductance? This would have the larger inductance. It's a very, very small amount of inductance. Okay, so if you short together some of the turns in an inductor, what ends up happening is you reduce the amount of turns in here. So if any of these get shorted together, you're essentially reducing the number of the turns. If I reduce the number of turns, I have less inductance. Okay. Also, if I space these coils further apart, if I don't have any shorts, but I space the coils further apart, I'll have less inductance. Now here's an interesting thing about inductors. In electronics, you don't have to have turns of wire to create inductance. Sometimes what you'll have is just what we call a ferrite or ceramic bead on the wire. Here's a picture of one. You've probably seen these on mice, these ferrite beads. They're encased in plastic. If you open it up, you can see the ferrite bead in there. But here's another one here too with many loops of turns in the ferrite bead. Ferrite beads act like an inductor. It's a good way to make an inductor without making turns of wire. So if you're working on a piece of radio frequency equipment, you see a ferrite bead in there, don't remove it. It's not to make it prettier for insulation. It's actually to create a type of inductor. How do you find total inductance of coils in parallel? Well, you just simply add them together because, no, hold on. Skip that, I'm sorry. In parallel, what we find is you find the total amount of inductance by utilizing the reciprocal formula. So how do you find inductors in parallel? Well, you take the reciprocal of each one, and you add them all together, and then you take the reciprocal. Finding the total inductance of coils in parallel is just like finding resistors in parallel, or capacitors in series, right? How do you find total inductance of the coils in series? With coils in series, you add them up because you're increasing the number of turns. Any time that you have inductors in series, 1, 2, 3, you're just adding, all you're doing is you're adding together the number of turns, more and more turns. When you add more and more turns, you're increasing the inductance. So inductors of coils in series, you just add them together. That's like resistors in series or capacitors in parallel. All right, last activity, believe it or not. The last activity sheet is about basic transformers. And first of all, what are transformers used for? Well, there's three purposes for transformers. You can use a transformer to increase AC voltage. You can use a transformer to decrease AC voltage. You can also use a transformer to isolate one circuit from another. You can isolate the current of one circuit from the current of another. What is the major construction of a transformer that determines the output voltage? Well, over here, it's the number of windings in the primary and the windings in the secondary. Generally, the turns ratio for this is written as the number of turns in the primary, double dots, the number of turns in the secondary. So this is a 10-to-1 ratio here. If that's what my transformer was here, then If I was putting 100 volts in, I have more turns in the primary. That would make me have less voltage on the secondary. So I would get, for 100 volts in, I would get 10 volts out. I'm gonna risk telling you that any transformer you see on the CET or employee entry examination most likely would be a step down. Now, if you're going into the power distribution industry, you might see step-up transformers, but generally about 80 or 90% are step down. So all you need to do is divide it by the turns ratio to get the divide it by the number in the turns ratio to actually get the voltage on the output. How is the voltage increased from primary to secondary? You increase the number of turns in the secondary compared to the primary. How is the voltage decreased for primary to secondary? You decrease the number of turns in the secondary. And that shows up right here. In a step down, you would have 10 to 1. That would be a step down. 1 turn in the secondary for every 10 turns in the primary. A step up, though, would be 1 to 10. You have 10 times the amount of turns in the secondary that you have in the primary. Okay, now, what are the 3 resistive or continuity checks that you can perform? Well, first of all, I was concerned because a few of you missed the question about continuity. What is a continuity check? A continuity check is using an ohm meter. How would you check the continuity of a transformer to make sure it's okay? Well, we have an inductor in the primary, and if I check between here and here with my ohm meter, it should read very, very low because it's just turns of wires in there. But if I read from here, primary to secondary, I should get infinity ohms because there's no direct electrical connection between here and there. You're passing electromagnetic flux or lines of magnetic force between them, but there's no direct electrical connection there. So the 3 checks, primary to primary, low, secondary to secondary, low, and anyone on the primary to anyone on the secondary should be high. Those are the 3 resistive or continuity checks. If you're using a beeper function on your meter, it would beep from here to here. It would beep from here to here. That's continuity. It would not beep from here to there. All right, transformers work on the concept of mutual induction. When I put voltage into this primary, electromagnetic lines of flux or lines of force build up and cut through the coils of the secondary. And that's what generates the voltage. You'll recall that Faraday and Lenz studied this idea of transformers, and Faraday said that if lines of force cut through a wire, you're going to generate a voltage on there. And he also said that if you put current inside of an inductor, it will generate lines of flux. So putting those 2 concepts together, we can actually create a transformer. That's why sometimes transformers are called isolation. They're not electrically connected to each other, but the lines of flux is what creates the electricity in the secondary. This is generating lines of flux, and this is generating voltage from lines of flux. All right, here's a confusing question about the core. The core is used to increase the inductance of a coil or to make a transformer more efficient. But you have to be careful with this question. The metal core does not actually increase the number of lines of flux. The lines of flux are determined by the current flowing in the coil. All the core does is focus, direct, and control the existing lines of flux. So over here you can see I have 1, 2, 3, 4, 5, 6, 7. In reality, in this one here on the left, if it's the same current flowing in there, I actually do have 7. There's 3, 4, 5, 6, 7. There's a total of 7 lines of flux there. What the core does, when you put the core in there, the core will actually pull these magnetic lines of flux down and focus them and direct or control them into a tighter place. A core works just like a magnifying glass with sunlight. It's not increasing the sunlight, it's increasing the density of the sunlight. It's pulling it together into a smaller spot. So this is an odd question, and I see it on every CET exam. What is a metal core used for in a transformer? Some of the answers are to increase the number of lines of flux, which is not a good answer. And another answer would be to control, direct, or focus the lines of flux. That is the good answer. So watch for that one. It's a purposefully tricky question. All righty. One last couple of things here about transformers is the concept of eddy currents. And whenever you have a transformer with an iron core, it's constructed like this. You have a coil in the front end. You have an iron core in there, which the coil typically is wound on, but I'm going to draw it separately. And the situation with this is that an iron core actually is a conductor in its own right. And so when magnetic lines of flux build up here, trying to get over to this to cut through it, the magnetic lines of flux have to cut through the iron core as well. And guess what? You're not just generating electricity over here, but because this is a conductor, you're generating electricity inside of that as well. And the current that's generated in there, because the lines of flux actually cut through this this core on its way to the inductor. The lines of flux that are circling here cut through this core on its way to the inductor. You will generate current in there. And inside of that core is current flowing. The problem with that is it reduces the efficiency. The voltage and current that should be going on here, you lose some of it in the core. And they have a name for those. The term of endearment for the currents that develop inside of a metal core, and every metal core has it, they're called eddy currents. Now, eddy currents can be reduced by reducing the size of the conductor of the core. And the way that we do that is we take the core over here and we slice it up and put insulation between them. These are said to be laminations. There's laminations in there of insulation in there. And therefore, you're getting smaller, tiny currents in each of those little slices. A laminated core looks like this. You can actually see slices of metal, but there's this little plastic insulation in between them. It still works like one big core, but the eddy currents are minimized inside. And down here you can see, here's a laminated core, and in between these slices are insulation. So what are eddy currents? They're unwanted currents that develop inside of a metal core. How can eddy currents be reduced? By laminating the core or utilizing laminations in the core. That'll be your answer for that one. Now finally, why is frequency an important consideration with a transformer? Well, we talked about this before. What are transformers made out of? Hey, aren't they made out of inductors? Aren't transformers made out of inductors? And the number of ohms in an inductor of the primary, the secondary, X sub L is equal to 2 pi FL. Well, we have to be careful. Transformers are designed to work around a certain frequency. If you use a low-frequency transformer that is designed to have a very, very small amount of ohms in it at lower frequencies, when you increase the frequency, you're going to get a lot of ohms, and that'll restrict the amount of current that's flowing in that primary. So frequency is an important consideration with transformers because they're designed to work around a certain frequency. If I take a high-frequency transformer and run it with a very, very low frequency, my number of ohms of inductive reactance would be very low. I might overheat from overcurrent. If I take a very low-frequency transformer, like one designed for 60 hertz, and try to use it at audio frequencies about 1K, the X sub L might be so high, no current will flow in it. So they are frequency sensitive because transformers are built with inductors for primaries and secondaries, and the number of ohms in the inductor of AC ohms or reactance is equal to 2 pi FL. They're designed to work around certain frequencies. All right, looks like we're coming to the end here. And let's work with a couple of transformer problems here. I have a turns ratio up here of 10 to 1. And on the input of the transformer, I'm putting in 100 volts. How do I find the output? Well, first I have to identify this as a step down. Step down has a big number in the front and 1 in the second number. So I would take 100 volts RMS and divide it by 10. So my output for this transformer would be 10 volts RMS on the secondary. 10 volts RMS. So 10 volts RMS, because 100 divided by 10 is 10. Now here's something that you have to watch for. They'll try to fool you here sometimes with your AC units. There are two other units that are the same. There are two other units that are the same as volts RMS. Volts RMS, volts AC, and volts effective all mean the exact same thing. So 10 volts RMS is the same as 10 volts AC, is the same as 10 volts effective. Those all are the same unit. Don't be fooled by that on the test. They'll mix them and match them with you. They might say there's 10 volts AC coming into that transformer. What is the RMS on the secondary? Okay, so what if the output is 10 volts RMS? How would I find the peak voltage? Every exam that you take to get an interview, if they give you one, will have an RMS conversion on, so you need to know this. So how do I find the peak voltage from RMS? Well, I take the RMS and multiply it by 1.414. So 10 times 1.414, the peak voltage over here, from here to here, would be 14.1 volts. So from here to here, the peak voltage, that would be 14.1 volts. Watch your units, volts peak. And then how do I find peak to peak from there? Well, looking over here, we see peak to peak is from one peak to the other. So if peak is from here to here, I just multiply it by 2. So what would be the peak to peak value? The peak to peak value would be 28 volts, or 28.2 volts, or 28.3 volts. So make sure you can convert from RMS to peak to peak to peak, or peak to peak to RMS. You need to know how to do that. What I like to teach my students when I have them for second quarter is there's a hierarchy of units. And what I mean by that is the lowest number value is RMS. The next highest value for the same voltage is volts peak. The highest unit is numerical unit is volts peak to peak. So when you do your conversions, if your peak to peak voltage is not the largest and your VRMS is not the smallest, you've got a problem. I call this the hierarchy of units for AC. All right, let's do a practice quiz. Get your practice quiz out and take a look at it. Okay, oh my, this is a discharge curve. So for one time constant, what is the percent of the voltage? Well, you might recall during discharge when we talked about time constant that it was 37% for one time constant. And I'm looking over here, see if you can pick this out. Right here is 3.7 volts, and the original was 10. Well, 3.7 over 10 is what percent? Well, no kidding. It's 37%. And 37% is how many time constants? 1. So I have one time constant tau is equal to RC. And it says how long does it take? 14 milliseconds. So 14 milliseconds is equal to R times C. But what is given? R is 4.7K. So 4,700 times C. Now how do I solve that? 14 milliseconds divided by C. Do it. Do it on your calculator. Do it on your calculator. 14 milliseconds divided by 4,700. So 0.014 divided by 4,700. Well, look, I got 2.99 microfarads. Now look, none of these say 2.99, do they? But you better guess the one that is really the closest, because on my calculator, it says 2.98. So what's the correct answer here? 2.98 microfarads. Watch your engineering notation. The correct answer for this one is 2.98 microfarads. Okay. Whether charging or discharging, at which time constant is the current flow from the capacitor at its maximum? Well, we learned earlier in this PowerPoint that the maximum occurs during the 0 and first time constant, and the minimum occurs at the 5th time constant. So what is the correct answer here? Whether charge or discharge, maximum occurrence happens between the 0 and first time constant. All right. An inductor has some of its coils shorted together due to excess heat. What happens to the inductance? Well, when you short coils together, you effectively reduce the number of coils. What happens to the inductance if I reduce the number of coils? Well, the inductance decreases. The inductance decreases. The answer would be C for this one. In a capacitor, what happens to the capacitance as the plates are made smaller? Well, if they're smaller, they can't hold as many electrons. And the number of electrons is the charge. So if they're made smaller, the charge is reduced and the microfarad is reduced. So what is your answer for this one? The answer is decreases. Okay. Now here's a straight up one here. Notice there's a lot of these questions here that revolve around time constants. You're going to have to see at least 4 of them. You're going to have to master that. That's 4% of your test. You can get every one wrong and still get a 96%, but that means you've got to get every single other one right. You need a 75% to pass the CET. Okay. The key phrase here is about 63%. Well, how many time constants is 63% for charging? Well, that's 1 time constant. So my answer for this would be 1 time constant. If this question said 100%, what would you say? If it said 100%, you would have to say 5 time constants. All right, total capacitance of capacitors connected in parallel can be calculated the same manner as, well, caps in parallel, I add them together. What other component can I add together? What other component in what kind of circuit would be series or parallel? Well, capacitors in series, no, that's reciprocal. Resistors in series, no, that's reciprocal. Inductors, yeah, that's reciprocal. So the only one here is resistors in parallel are added together. Resistors in series are added together, rather. Resistors in series. So resistors in series, you add them together, that's how you do the same thing as caps in parallel. Okay, look at number 7 here. After 5 time constants, what happens to the current flow? Well, here we go. Remember, they're going to check you on 1 and 5. Current is maximum from 0 to first time constant, and current is minimum on the 5th time constant. So what happens to the current flow when the DC voltage across the cap is approximately equal to the source charging it after 5 time constants? Well, look at this tricky one here. Current flow is optimized. Well, that's stupid. That's a stupid answer. It sounds good, but it's not a good answer. What does optimized mean? Does it mean minimum or max? We have no idea. Well, the only thing that's left is we know current's not maximum, and it's not maximum from the source because the current in the cap and the current on the source is the same. And the cap, it may or may not be damaged. I don't know. I don't have enough information. So the only possible answer here is B. Little or no current flows. Watch out for this one. This one about this optimized. This is a purposely tricky question to see if you know what you're talking about. Okay. Look at this. This is a good one. In the diagram below, and remember, this is an AC or DC source. It makes no difference. The source is 40 volts. C1 is 2 microfarad, and C2 is 4 microfarads. So which capacitor is the smallest? That one. C1 is the smallest. Now, what did we say about the smallest capacitor? It has to have the larger voltage. Don't worry about doing math here. You can do math and find it. But it'll take you too long. Look for the answer that tells you it's the smallest cap has the larger voltage. Okay, well I have 40 volts applied, don't I? So these two voltages added up have to be equal to 40 because that's Kirchhoff's voltage law. Let's look at these answers. Well, can I have 13 volts on the 2 microfarad? The 2 microfarad is here, and the total voltage is 40. That seems like less than half. That's a smaller voltage, so I don't want that one. What about this one, 20 volts across each? The voltage won't be the same on each of these because they're different microfarads. Different microfarads will give you different voltages. That still doesn't answer the question about the smallest cap with the larger voltage. 100 volts across each, no. Well, first of all, the voltage won't be the same, and second of all, you only have 40 volts applied, so that can't be it. 40 volts on the 4 microfarad and 20 volts on the 2 microfarad. No, because 40 and 20 is 60. I only have 40 applied. Plus, this shows a smaller voltage on the smaller cap, which is not right. The only possible answer here, would be B, 27 volts across the 2 microfarad. Why? The 2 microfarad is the smaller cap. It's going to have more than half of the voltage in this case. So watch for that. Okay, what are eddy currents? Well, we just covered that. It should be fresh in your mind. Eddy currents, what are those? Well, are they currents inside the coils of an inductor or transformer? No. Are they the laminations in the inductor or transformer? No. They're not the laminations. Are they the current inside of the capacitor? No. Are they the unwanted current that develops in an inductor or transformer's metal core? Yes. We talked about it in reference to transformers. You don't want current in the metal core. And by the way, the associated question with this is, what can you do to reduce eddy currents? Well, even though this is the correct answer for this question, what we'll see with the associated question is, eddy currents can be reduced in the transformer by laminating the core. Okay, so watch for that one too as well. It's one of two variations. All right, I think that pretty much wraps up what we have to do here. And so for your homework, you're aware now that not all the documents are released at the same time. You have to kind of check every other day for what's being released on the Blackboard site. For example, I gave you the activity sheets, but I didn't give you the answers to them. I want you to watch the video for the, for the idiosyncrasies and the heads up on the special language. You probably wouldn't pass the CET just by looking at the answers on the activity sheet. That's why I want you to watch the video. Research has shown that you got to watch the video along with doing the activity sheets. So not all the handouts are released at the same time. The online quiz is the last thing that gets released. It has to be done by Monday. Some of you have not done the online quiz. I had to give you a 0. The practice quiz, I'll release that today. I'll release that in a couple of days. And the answer to the activity sheets I'll release in a couple of days, probably Thursday or Friday. Okay, so all those things reduced at different, they're released to you at different times. And then I'll turn the quiz on Friday. And then you can get on the quiz and finish it up by Monday. You have to do the quiz over the weekend. Now remember, if you are interested in taking the CET, you should be creating a test bank of practice and real quizzes. And the way that you study that is you cross off the ones that you easily know and you study the ones you do not know. Those are the ones you need to know. Don't waste your time studying stuff that you already know. And then take those quizzes again. And then when you know those ones, cross them off. Don't go back. You know them. Eventually you're going to know all the answers to all the problems and quizzes. So do the online quiz by Monday. It's graded for week 2. And make sure you have the printouts ready to go for the next Collaborate video for week 3, which will appear sometime next Tuesday. So that's it for today. And thank you very much. I know it's a little bit difficult watching videos, especially listening to your Dr. McNeil here drone on and on like Charlie Brown's teacher. But this is the medium that we're given to try to help you to learn. It would be nice if you could come in and I could just teach you as a class one-on-one, but because some of us cannot come every night of the week, we have to do this over the internet. And we're doing it the best that we can. I'm always open for you to contact me via email if you have any questions. You should be striving to get 80% on every practice quiz or on every graded quiz. And at the end, we'll give you one big test that you can take, and then you can get an idea of how you do on it. And that will kind of be your go, no-go. Now, if you're not interested in taking the CET, you just got to take 6 online quizzes and get a 60% or higher, and I will pass you in the class. I would also like you to take the program outcomes test, which is actually one of the practice tests for the CET. Okay, so other than that, I'm done lecturing you, and thank you very much. Thanks for putting up with it, and I'll talk to you next week, if not sooner. Thank you.